You know, deep down, at the very heart of biology, there's this puzzle that's a lot like origami. Life is written in a simple, straight line of code called RNA. But for that code to actually do anything, it has to fold itself into these incredibly complex 3D machines. So the question is, how on earth does it know which way to fold?
And look, this isn't just some casual question. This is a puzzle that has absolutely stumped scientists for decades. I mean, they've thrown massive supercomputers at it, trying to simulate this whole process, but time and time again, the digital world just couldn't replicate what nature does so elegantly.
And this shot right here, it just perfectly illustrates the problem. You start with this simple string of information, and somehow the laws of physics have to guide it into a shape like this. A working, intricate, beautiful structure. You get just one fold wrong, and the whole biological machine can completely break down. For a computer, getting that right has seemed, well, pretty much impossible.
Okay, so to really get why this is such a huge breakthrough, you first have to understand the long history of failure. For years, trying to simulate this process was basically a recipe for digital disaster.
So, the goal was always simple, a perfect, stable fold. But the reality? It was just chaos. The simulations would either be so violent that they'd literally tear the molecular chains apart, kind of like an exploding pressure cooker, or they'd stretch the molecule out into this useless, endless line of spaghetti. It was a total mess.
And here's the kicker. Researchers were trapped. They were stuck in what they called a brutal trade-off. If they made the rules super strict to stop the molecule from breaking, well, it would just get stuck in one boring, useless shape. No creativity. But if they loosened the rules to try and find different shapes, the physics would just go haywire and the whole thing would collapse. It was a total dead end.
Until now, a new computational engine has just arrived on the scene, and it's promising to finally solve this impossible problem. It's called Cuteneta RNA, version 9.2.
And we're not just talking about some minor software update here. This thing was born out of what its creators literally called a deathmatch, a grueling 5-hour battle on some of the most advanced computer processors out there. And out of that computational fire, a whole new kind of engine emerged.
So what did it do? It achieved what they're calling the perfect balance. It finally found a way to maintain perfect physical integrity, so no more exploding chains, while also exploring a huge diversity of different structures. It solved that brutal trade-off.
All right, so those are some pretty big claims. They need some big proof to back them up, right? Well, the data from the engine's very first run reveals what its creators call 3 miraculous achievements. Let's put this thing to the test.
And for its first challenge, they didn't mess around. They went straight for the big boss, a massive RNA molecule they called the monster, named 9-MME. We're talking about a puzzle with 4,640 individual pieces. This was the ultimate stress test.
Okay, let's take a look at the data here, because this is where it gets really interesting. RG, that's just the molecule size. CL stands for clashes, basically how many times the molecule crashed into itself. But BD, that's the one you really got to watch. It stands for bond breaks. It tells us how many times the chain physically snapped. So for this absolute monster of a molecule, the number of bond breaks was
0, that's right, 0. Over 4,600 pieces twisting and folding under these immense simulated forces and not a single bone fracture. That whole exploding pressure cooker problem? Solved. This was completely unheard of.
Okay, so it didn't break. Awesome. But remember that other problem, the endless spaghetti? That was the second major test for the engine, taming what they called the Great Expansion.
This chart really says it all. In the older models, this 9-MME molecule would just stretch out to this absurd size of over 1,500 angstroms. But KUT-RNA, it totally contained it, bringing it back down to a realistic, functional size. It literally turned the digital spaghetti back into a real structure. So, the structure is strong, and it's the right size. You'd think that's it, right? But there was one final, more subtle challenge, one that plagues pretty much all modern AI systems. It's this problem called mode collapse. And, you know, it's basically when an AI gets lazy. It finds one good enough answer, and then it just gives you that same answer over and over and over again, never bothering to explore other, maybe even better solutions.
And this is where QT-RNA just showed its genius. When they asked it to fold the same molecule multiple times, it didn't get stuck. For instance, here are just 2 of the 5 completely different, unique structures it created from the exact same code. And every single one was physically perfect. No breaks, no clashes. This wasn't a bug, it was a feature. It had totally conquered mode collapse and generated this rich portfolio of possible answers.
So, with these three massive achievements, the engine had proven itself. It was strong, it was stable, and it was creative. The work on the physics model itself was done. It was time for the final judgment.
The creators are pretty sure that this purely physics-based model has gone as far as it can go. It's reached its absolute peak. So there's only one thing left to do. Hit that Submit to Competition button and see how it stacks up against the rest of the world.
And that leads us to the pivotal question, right? What happens now? What does this final test really, truly mean for science?
And this is the brilliant part. It's a win-win. If the model gets a high score in the competition, that's an incredible victory. It proves that this puzzle can be solved with physics alone. But if it gets a low score, that's not a failure. It's a totally different kind of discovery. It's proof that physics alone isn't enough, which opens the door to a whole new world of research.
So you see, no matter what the outcome is, a monumental step forward has already been taken. We've either found the answer, or we've just discovered a much deeper, more interesting question to ask.
And as the creators themselves put it, that's the real victory here. The door to a new dimension of understanding has just been kicked wide open.
And that leaves us with one final thought to chew on. Is this the end of a chapter? The absolute limit of what pure physics can tell us about the machinery of life? Or is it the beginning of a brand new book? A new way of finally understanding it all?